Welcome to the video on periodic trends. Up until now, we've been discussing individual atoms and the electrons of those atoms and how those electrons look. Now we're going to be discussing the entire periodic table and how do different things change from element to element as you go across the periodic table, you go down the periodic table, and that sort of thing. There's several vocabulary words that you need to know, 6 of them, for this particular section. Electron shielding is the first one. That is when the inner electrons, the core electrons, block some of the force of the nucleus, the protons in the nucleus, because you know electrons are negative, protons are positive, so they're attracting to each other. So those protons are pulling on the electrons, and the inner electrons are able to block some of that pull from the outer electrons. That's called electron shielding. The electron shielding results in something called effective nuclear charge, which is that those outer electrons, since they're not feeling the full force of the nucleus, how much force are they feeling? And you can calculate that. Electron shielding works kind of the same way as if you had a row of people. So let's say we had 3 people. Some of them have rather large heads. Okay, person 1, person 2, person 3. And over here, we have a fan. Okay, the fan is blowing, and person 1 is feeling the greatest effect of that force, the force of that wind. Person 2 is shielded from some of the force of that wind by person 1, and person 3 is feeling the least amount of that wind because it's being blocked by both 1 and 2, so it has the most shielding. And so then if this was in terms of charge, and this was the nucleus, this is the nucleus, and these are electrons in different energy levels, energy level 1, energy level 2, energy level 3, then the electrons in the first energy level are feeling the greatest attractive force. And the electrons in energy level 2 are feeling less, and electrons in energy level 3, which we are valence electrons, are feeling the least amount of force. Okay, let's look at that in terms of an actual picture of electrons and atoms. Don't worry, I'll slide the board back over so you can copy the rest of those definitions. All right. Here are the 3p elements. All of these guys are in the 3rd energy level and in the p subshell. For the purposes of periodic trends, you do not have to worry about breaking down the energy levels into their various subshells. So we're going to go back to the Bohr diagram because the Bohr models just have the energy levels, and that's the most important part as far as what we're going to talk about right now. For aluminum, has 13 protons. So there are 13 positive charges in the nucleus pulling the negative electrons in toward the nucleus. The stronger the protons can pull it in, the smaller that atom is going to be. So let's talk about the electron shielding that's going on here. In our first energy level, we have 2 electrons. Those electrons, there is nothing between them and the nucleus except for empty space, and so they are feeling the full force of that nucleus. So their effective nuclear charge is 13. They're feeling the force of 13 protons. So green is the effective nuclear charge. And so for the first inner shell, that's going to be 13. First energy level. For the second energy level, the first 2 electrons are shielding 1 proton's worth of force apiece. So since there's 2 electrons, they're shielding 2 protons worth of force total. So these guys feel 11. And that's true for these guys, and these guys, and these guys, and these guys. All 8 electrons on aluminum's second energy level are feeling the force of 11 protons. So 11 for the second energy level. Now the 3rd energy level, the valence shell, is being shielded by both the first energy level electrons and the second energy level electrons. So that's a total of 10 electrons between them and the nucleus. So therefore, they are only feeling 3 protons worth of force. 3 for the 3rd energy level. So if we want to talk about the effective nuclear charge of the various electrons on aluminum, they have either 13, 11, or 3, depending on how far away they are from the nucleus. And you can do that for all of these guys. The first ones on the inner shell feel the force of all the protons. The second one is all protons minus 2. And then the third one is all protons minus 10 because you have 10 electrons in between them and everything else. So these guys, the valence shell feel a force of 4. This is 14 minus 10. These guys feel a force of 5, 6, 7, and 8. Okay, so that is electron shielding and the effective nuclear charge that results from electron shielding. So the forces that these electrons feel will have an effect on the, first of all, the physical properties of the atom, and then also the chemical properties of the atom. So how does the atom look, and then how does the atom interact with other atoms? And that's the 4 periodic trends. I'm going to slide the board back. The 4 periodic trends that we need to discuss. First periodic trend, atomic radius. It's the same as any radius of any circle. Basically, the atom's a sphere, so the radius is the distance from the center of that sphere, which in the case of an atom is the nucleus, to the outermost edge of the sphere, which in this case would be the valence electrons. Ionic radius is the same thing, but we're talking about an ion. Electronegativity, the propensity for an atom to attract a pair of shared electrons. Good SAT word for you, propensity. It means the likelihood or the tendency to do something. So what is the likelihood of a sulfur atom to attract electrons away from another atom when they're sharing them? And they share them when they make chemical bonds. We're going to talk more about that when we get to Unit 7. Okay? But for right now, we're just going to know what the electronegativity does. And ionization energy is the energy required to yank an electron away from an atom, therefore making it an ion. And it would be a cation because it's positive, because it's loss of electron. Now for ionization energy, there are first ionization energy. So that's how much energy it takes to pull away the first electron. There's the second ionization energy. So once you've already pulled away one electron, how much energy does it take you to pull away another electron, and so on and so forth. You have third ionization energy, fourth ionization energy, and up to all the electrons. But we usually don't talk about first and the second. Okay, let's talk about how these things will be affected. So atomic radius, as you go from hydrogen to lithium to sodium to potassium to rubidium, you are adding energy levels. So therefore, atomic radius is going to increase. I'm actually going to erase this. The atomic radius, which will be done in green, is going to increase as you go down the periodic table, meaning that francium is bigger than hydrogen. This makes a lot of sense. Now, how about as you go across the periodic table? Well, let's go back and look at our 3p atoms again. So we have said that the outermost electrons are feeling different amounts of force in these different atoms. The ones that feel the most force, so that force means that the protons are pulling the electrons in. So the more the protons can pull the electrons in, the smaller that atom is going to be. So if this is pulling these electrons, if argon is pulling its valence electrons in with a force of 8, then it is going to be smaller than chlorine, which is only pulling in with a force of 7. But chlorine is going to be smaller than sulfur, which is only pulling in with a force of 6. So this would be the smallest, and this would be the biggest. Because it's only able to pull its outermost electrons in with a force of 3. Notice they all have the same number of energy levels, so that's not going to affect their size. The only thing affecting their size is their effective nuclear charge, meaning how well they can pull in those outermost electrons. So, to go back to our periodic table, the atomic radius increases as you go left on the periodic table. In fact, I'm going to go ahead and erase this. So use space for that. All right, so the bigger atoms are the ones on the left, which is somewhat counterintuitive because people usually are thinking, well, if this has 5 and that has 6 and that has 7, we're increasing our numbers of protons and electrons, but we're actually decreasing the size because those other electrons are going in the same energy level, but the protons, the nucleus is getting bigger and stronger, and so it's able to pull those electrons in better. Okay, let's talk about ionic radius. That'll be done in purple. Speaking of which, on your periodic table, please draw these arrows. Now, when you get to the test, you're not going to have those arrows, so you're going to know what they are by the time you get to the test. But for now, draw those arrows. Okay, how big is an ion? Well, again, as we go down the periodic table, we are increasing our number of energy levels, and therefore, ionic radius does the exact same thing as atomic radius. All right, what about going across? Well, let's make some ions out of these guys. Okay, I'm going to erase this. Aluminum is +3, so therefore when it becomes an ion, it takes away 3 electrons, which will remove its outermost shell completely, and now its outermost electrons are feeling the force of 11. Silicon is a +4, so it's going to take away all these electrons, and so its outermost valence shell are feeling a total of 12 force. Now, phosphorus is an anion, so it's going to add 3 electrons. And those 3 electrons are still feeling the force of 5. Now, the force of 5 is being distributed among 8 electrons instead of 5 electrons, so it's going to be a little bit weaker. So it's going to be somewhat less than 5. Sulfur is going to be adding 2 electrons. I'm sorry, sulfur didn't have the right number to start with. There should have been one more here. Okay. Sulfur's going to be adding 2. 1, 2. It'll be feeling somewhat less than 6. And chlorine is going to add 1 more, so it'll be feeling somewhat less than 7. Now, this will be even more less than, and this will be a little bit medium less than, and that will just be a little bit less than because we're only adding 1 more electron. Now, argon doesn't make an ion at all, so we don't care about those. So for ionic radius, we're not even going to discuss the noble gases at all because they don't make ions. So therefore, we have 11, 12, 5, a little bit less than 5, a little less than 6, a little bit less than 7. So if this one's feeling 11, then this will have to be the smallest. I'm sorry, if this one's feeling 11, this one's feeling 12. This is the most of this feeling, so this one will be the smallest. And then this one will be bigger than that. Bigger than silicon. However, this will be smaller than these guys, because these guys are feeling less force. So this will be the biggest. And this will be smaller than phosphorus and sulfur, but it is still bigger than silicon and aluminum. Silicon. So we have a kind of dichotomy happening here as far as whether or not you are a cation or you are an anion. So this is aluminum +3, this is silicon +4, this is phosphorus -3, sulfur -2, or -1. So let's go back to our periodic table. So what's going on here is that there's a dichotomy, as I said, between the anions and the cations. So as the anions go left to right, they are getting bigger. Oh, I should have included noble gases here. I'm going to include the noble gases for atoms. I'm not going to include them for ions. So the anions get bigger as you go left until you get to here, where the anions stop. And then the cations are small again. These are way smaller than these, and get bigger again as you go left across the periodic table. So it's kind of the same way as atomic radius, but there's a split between the cations and the anions. Sorry, I'm going to do that the right way. All right, next one, electronegativity. What's the likelihood of an atom to attract somebody else's? Well, that has to do, again, with your effective nuclear charge. The more pull your own valence electrons are feeling, the more the nucleus can attract somebody else's valence electrons. So when you have a small atom, you have a large electronegativity, meaning that smaller atoms have a lot more force to them, and so can pull somebody else's. If you have a large atom, then you're going to have low electronegativity because they're having a hard time holding on to their own electrons, so they're not quite as capable of pulling away somebody else's. So let's add that. So we're going to do that in red. So therefore, if you have large atoms, they have low electronegativity. So the electronegativity increases as the atoms get smaller. And so these, the electronegativity arrow, is exactly the opposite. I'm sorry, I should have stopped that again here, okay, before we get to the middle gases. So the electronegativity is exactly the opposite of atomic radius. Ionization energy is the same as electronegativity. We'll do that blue. So ionization energy increases as the atoms get smaller. That one actually does go all the way. And again, ionization energy is the energy required to remove an electron from the atom. So the harder, the more forcefully you're holding on to your own electrons, the harder it is to take them away. So if I'm holding on to my electron really tightly, because I have a high effective nuclear charge, then it is really hard to take that electron away. And then you have a really big atom, it's got a very small effective nuclear charge on its valence shell, so therefore it's easy to take the atom, the electron away from that atom. And so ionization energy is also opposite of size. And in class we'll be discussing these in a little bit more detail. Thank you.